Hi ladies and gentlemen, today we're taking a look at B.3 compound events. So today we will find the sample space of two or more events, find the total number of possible outcomes of two or more events, and find the probabilities of compound events. Starting off, I have a little bit of a typo in our notes, so please bear with me as I go through and fix those. So the first is, this first definition should not be for sample space. It should really be for fundamental counting principle. Right, and then also this here with the probability computation is not needed for this either. So a couple of errors there, so I apologize for that. Our definition that we have here, I know my screen's cutting it off a little bit, but it's where you multiply the number of possible outcomes from one event by the number of possible outcomes of another event. We're going to be going through examples of this in the notes when we take a look at example 3. Kind of the overarching theme of what we're going to be doing is you're basically looking at all of your options for one event times all the options of your other event. All right, the next one, which I know this one says fundamental counting principle, but I already had the definition typed on that last slide. So we're going to change this one to be the probability, to be sample space. So this is going to be the definition for sample space, and it is the set of all possible outcomes. And when we look at examples 1 and 2 in the notes, we'll be going through finding sample space. And last is compound events. That's looking at two or more events. We'll be going through compound events when we look at examples 4 and 5. When finding the probability of compound events, we always use our probability notation. So capital P inside the parentheses is the event equals your number of favorable outcomes. Divided by your total number of all possible outcomes. All right, so let's get on to some examples. So example 1 with finding sample space. With finding a sample space, there's a couple of ways you can go about it. So in example 1, I'm going to go through and show you how you can use a tree diagram to find a sample space. In example 2, I'm going to show you how you can use a table to find a sample space. Again, these are just two methods. If you have another method that you like better, and as long as it's showing your work and your thought process, that's fine too. So in example 1, it says find the sample space for the number of different sandwiches that are possible. Well, we have two bread options, wheat and sourdough, and then we have 4 types of sandwiches: ham, turkey, steak, and chicken. So what I'm going to do is I'm going to start off with my tree diagram by identifying one category for the wheat bread and one for the sourdough bread. So I have wheat, and then I'm going to use SD to shorthand sourdough. And then I have the turkey, the ham, the steak, and the chicken option with the wheat bread. And then I also have those same options with the sourdough bread. So now what we can do is we can look at all of our potential outcomes. Well, we have the outcome of wheat and turkey. We have the outcome of wheat and ham, wheat and steak, and wheat and chicken. So there's 4 options there with the wheat bread. We also have 4 options with the sourdough bread, because you could do sourdough ham, sourdough turkey, sourdough steak, and sourdough with chicken. So that's a total of 8 different sandwiches possible. So this is how you could use a tree diagram to help give you a visual of the different types of sandwiches you can make. Now let's take a look at using a table to look at all of your number of possible outcomes, or in other words, finding your sample space. So this problem says find the total number of possible outcomes of rolling a number cube and flipping a coin. So to create our table, one part of our table is going to represent all the numbers we could get. So 1, 2, 3, 4, 5, and 6. And the other part of our table is going to represent all the ways we could flip the coin, so getting heads or tails. So filling in our table with all these matchups, I could get a heads in the number 1 or tails in a number 1 on the coin, or on the number cube. I could get a heads on the coin and a 2 on the number cube, a heads and a 3, heads and 4, heads and 5, heads and 6, or I could get each of those numbers but with tails. Well, counting up all of these cells of all these different matchups I could get for the number cube and the coin, I get a total of 12 total possible outcomes for rolling a cube and flipping a coin. So finding your total sample space or total number of outcomes, you can create a tree diagram, you could create a table, and the last option of what you can do is to use the fundamental counting principle, and that's what we're going to look at in example 3. So in example 3, find the total number of possible outcomes. How many different outfits can you make from the t-shirts, jeans, and shoes in the closet? Now, if you don't have a colored copy of notes, I know that this is a little bit difficult to read, the closet here, and to count all the things. So again, this is an example using the fundamental counting principle, so we might want to write that down. So when you're looking back at your notes, you can see that. When we're using the fundamental counting principle, we need to figure out how many we have of each category. So in our closet, we have 4 options for our jeans. For our t-shirts, we have 7 options. And for our shoes, we have 3 options. The way we use the fundamental counting principle, instead of creating a table or a tree diagram, we take the number of options from each category and multiply them together. So that means I'm going to take 4 times 7 times 3, that's 84. So that means I have 84 different outfits that can be made. Right, so to find our total sample space, there are 3 options: table, tree diagram, and fundamental counting principle. Watch the next video to see the last few examples.